Okay, this is the exam 3 from MA 161. This is from the fall 2022 semester. These exam 3 types, it's largely just a lot of applications of derivatives. So things like concavity, increasing and decreasing, related rates, just building on a lot of stuff that you did in the exam 2s, a lot of just finding derivatives like your product rule and your chain rule. So it's kind of a lot of word problems of derivatives and things relating to derivatives. So if you're good with the exam 2s, then this shouldn't be too bad. Question 1 is a really good example of that. So it's asking when this f of x here on this domain is concave downward. So concavity, that just is kind of it's kind of related to increasing and decreasing, but on the next derivative. So an example that I've drawn out here, this isn't what f of x looks like. This is just a random example. If we have on this function, it's concave downwards on this interval, and then stops right about there, and it's concave upwards on this interval. So you'll see here on this first one here, it's concave downwards because it's always got this this I don't I don't really know a good English word for it, but you can see it's sort of going downwards, but just in a different way. Technically, it's increasing right here. In fact, it would have a critical point right there, but across this entire interval is concave downwards. And the opposite is true over here. You can see it's always kind of going upwards. So that is concave upwards on that interval following this point. And this point has a special name. It's called an inflection point. It's kind of related to critical points, in which we'd have two here. We'd have one right there and right there. But they're a little bit different, though you do find them pretty similarly. So this is a question all about concavity when something is concave downwards. And to find that, so you know how with critical points, you take the first derivative of your f of x and then set it equal to 0. Well, for inflection points, you take the second derivative and set it equal to 0. So first off, finding that second derivative, we're going to have to do two derivatives. So if our f of x is x squared minus 4 times cosine x, our first derivative, f prime of x, that's going to be 2x minus, this cosine is going to become negative sine, so that's going to be plus 4 sine x. And then now our second derivative, f double prime of x, that's going to be 2 plus 4 cosine x. So that's our second derivative. Now setting it equal to 0 and then solving for x, we will get, first we could subtract 2 from both sides, so negative 2 equals 4 times cosine x, and then divide both sides by 4, we get negative 2 fourths, which is a half. Negative 1/2 equals cosine of x. So we technically have an infinite number of solutions here. There's going to be an infinite number of values we can plug in for x that will make this true, since it's a cosine function, and those look like that. So infinite number of solutions. But fortunately, this is defined on a restricted domain just from the values when x is between 0 and 2 pi. So we'll only have a couple of solutions. Now, when cosine equals negative 1/2, you could either use the unit circle values table to figure that out, or just kind of do it visually. So if you have your unit circle and you're trying to find when the cosine equals negative 1/2, well, remember that cosine for any angle, imagine our angle is this, cosine measures this distance right here, this horizontal distance. So if we want that to equal negative 1/2, it would go left, and it would be 1/2, so exactly right in the middle right there. So if we draw a line upwards, going all the way up and all the way down, put our points where they intersect, and then draw our angles, that's where they're going to be. And visually, you can kind of tell that the first angle is going to be 2 pi over 3. This one is 2 pi over 3. And then we have another one going a little more around. That one is going to be 4 pi over 3. So that is the two x values that we have. And those are our two possible inflection points. I say possible because sometimes functions can be tricky, and the inflection point that you give here isn't actually an inflection point. So we do have to do a little more vetting to make sure these are actually inflection points, and then also find out which intervals are concave upwards and downwards. But just based off of these two answer choices, we can already rule out a ton of answer choices we have on the left here. So since these are the only possible inflection points, we can kind of rule out any other answer choice that does not have 0, 2 pi over 3, 4 pi over 3, or 2 pi. So we can automatically rule out A, C, and E because they all have pi over 3 in it. So we're just left with B and D. Those do look like what we're trying to find because they all only involve the values that we just said. So now to actually find those points, we'd use that big T chart that we typically do for critical points. So on the left, we have our key X values and some intermediary values. And then on the right, we have our output. So on the left, we have, let's see, we have 4 values to worry about, counting the domain endpoints. So we've got 0, then it's going to be 2 pi over 3, then 4 pi over 3, and then finally 2 pi. Some good intermediary values for those would probably be pi over 3, pi, and 5 pi over 3. Those look pretty easy. And then for our output, so typically for critical points, since that involves setting f prime equal to 0, you put f prime up there, but since we set f double prime equal to 0, we're actually going to use f double prime for our output. So plugging in all of these values for x now, keep in mind that 4 of these we've already figured out. These are all going to be 0 here. Those are the key potential inflection points. And now for the intermediary ones, so pi over 3, plugging that in, cosine of pi over 3, that's going to be 1/2. Half times 4 is 2. 2 plus 2 is 4. That's positive. Doing pi now, cosine of pi is -1. -1 times 4 is -4. -4 plus 2 is -2, so that is negative. And then finally 5 pi over 3. So cosine of 5 pi over 3, that's going to be also 1/2, and that's just going to result in the same answer as pi over 3. That's going to be positive. So now that we have all of these pluses and minuses and zeros, what do those tell us? So since we're looking for the intervals where f of x is concave downward, we need to find intervals where there is a negative, a minus sign. And it looks like we only have one of those. It's the interval from 2 pi over 3 to 4 pi over 3, in which there is a concavity that is negative. So our answer choice is going to be B. Question 2. A certain function f of x has the following first derivative right here. How many local minima does f of x have? All right, so local minima and local maxima, those are easier to understand than inflection points. So this is just an example function. Local maxima are these, and local minima are these. Pretty standard stuff. So we know how to solve these. We just set f of x equal to 0, and fortunately they've already given us our f prime of x, so we just have to plug that in and then solve for x. So this will be 0 equals x squared times x minus 4 times x minus 2 times x plus 2 squared. So okay, we can split this into a bunch of different functions now. So we've got x squared equals 0, we've got x minus 4 equals 0, we've got x minus 2 equals 0, and x plus 2 squared equals 0. That is our potential critical points. So solving each one of these, this will give us x equals 0, x equals 4, x equals 2, and x equals -2. Awesome. Yeah, cool. So these are our potential critical points. These could either be maxima or minima, and we need to find the number of minima. So to vet these, we go ahead and set up our T-chart. So this is going to have our input values on the left and our output values on the right. Since we're finding critical points, we're going to use f prime of x for our output. Now plugging in all of these values, we have 0, 4, 2, and -2. And then some intermediary values that would be good. Oh, actually, I kind of messed this up. These need to go in order. So this is going to be -2, 0, 2, and 4. And then maybe we could do -1, 1, and 3. Cool. So now we have to find f prime of x for all 7 of these values. That sounds like a lot, but as always, half of these are already filled in for us. This 4 of them are just going to be equal to 0. So you've got those 4 we already talked about. Those are already done. And on top of that, for the values that we actually do have to calculate, we're only concerned with its sign at the end of it all. So we're only concerned if it's going to be positive or negative at the end. So sometimes we can take a few shortcuts if we know how the problem is going. So starting this off, let's do -1. So f prime of -1, that's going to be, okay, that's going to be a lot. So we basically have 4 terms to worry about. So we can basically just find the sign of each one of these 4 terms, and then we'll be good from there. So, and even less than that actually, because 2 of these terms are squared, and those are always going to be positive. So this term and that term are positive. Now for the middle 2, -1 minus 4 is -5, and -1 minus 2 is -3. So we have a positive times a negative times a negative times a positive. That is a positive. Now moving on to +1, f prime of +1. This is going to be, so we've got positives at the end. That's not going to do anything. 1 minus 4 is -3. 1 minus 2 is also negative. So this is going to be positive. And then moving on to our last one, we've got 3, +3. F prime of 3 equals, same thing again. Outside terms are positive, and then the inside terms. So 3 minus 4 is -1, and 3 minus 2 is +1. So since we've got 3 positives which don't do anything and an odd number of negatives, this is going to leave us with a negative answer. Negative right there. And since we're concerned with the number of local minima, we're trying to find the intervals in which we have a negative sign, in which we have a minus. And we have 1. It's right down there. We have a minus surrounded by our 2 critical points, so we know we only have 1 local minima. Answer choice D. Question 3. Consider the function f of x equals x to the 6th over 30 minus x to the 4th all over 12. How many inflection points does f of x have? Cool. So inflection points, what we do for those is we first find f double prime of x and then set it equal to 0 and then solve for x after we find all that. So finding f double prime of x, that's going to require us finding f prime of x. So that's going to be taking the derivative of x to the 6th all over 30, bring the 6 out front, and then minus it by 1. So that's going to be 6x to the 5th all over 30. That is just x to the 5th over 5, all things considered. Now for the second one, it's largely the same thing. We move the 4 out to the front, and then subtract it by 1. That's going to be 4x cubed all over 12. That's the same as x cubed over 3. All right, so now we have our f prime of x. Now to find our f double prime of x, let's see, same logic here. We move the 5 out to the front and then subtract it by 1. So it's going to be 5x to the 4th all over 5. That's the same as x to the 4th. Those 5s are going to cancel out. And then the same thing for the other one too. So we move the 3 out to the front and subtract by 1. That's going to be 3x squared over 3. The 3's cancel. We're just left with x squared. So we have our f double prime of x. Now we just set it equal to 0, and we move on. So we have 0 equals x to the 4th minus x squared. To solve for x, looks like we can take an x squared out of both of these terms. So that's going to leave us with 0 equals x squared times x squared minus 1. We can go ahead and split this off into 2 separate equations. So we've got our x squared term equals 0, and our x squared minus 1 term equals 0. So solving both of these independently, the left side is just going to give us x equals 0, and the right side is going to give us x squared equals 1, x equals plus and minus 1. So those are our three potential inflection points. Sometimes you can have less than that because sometimes some of these inflection points aren't actually inflection points. But what we do know is that there won't be more than 3 inflection points. This is the maximum number of inflection points that we'll have here. So we can rule out answer choice B already. So how to actually find these inflection intervals when we have the concavity changing. We set up our t-chart and then fill out our inputs and outputs. So we have our x on the left. Let's see, we're going to have -1, 0, and 1. And on the right, so since we're finding inflection points, since we were asked to set f double prime of x equal to 0, we're going to have f double prime of x on the top there to calculate our outputs. Oh, right. I forgot to fill in the intermediary values. So we've got values that we need to put here and here that are between all of these possible inflection points. Looks like we could probably do -1/2 and +1/2. That looks pretty easy. Now, calculating f double prime of x for all 5 of these. For 3 of them, we've already found that out. We set them equal to 0, so the 3 possible inflection points that we have are just going to be 0. So we only have to find 2 of these. So f double prime of -1/2, we'll start with that one. This is going to be equal to -1/2 to the 4th minus -1/2 squared. This is equal to, let's see, 1/2 to the 4th is 2, 4, 8, 16. It's going to be 1/16 minus 1/4. So this is going to be, I don't even know what the answer is going to be there, but it's definitely going to be negative. Unfortunately, that's all we're concerned about. We just need to find the signage of the outputs of all of these. So we have our work kind of cut out for us already. And now f double prime of +1/2, that's the last x value that we need to find. That's going to be the exact same thing. So take note that both of these exponents are even, so that's going to make anything you put into it positive. So after we do this first step, we're going to be left with the same thing. It's going to be 1/16 minus 1/4. We've already found that's going to be negative, so we're going to put a negative right there. Now, the last step in finding the total number of inflection points that we have is just to rule out all of the inflection points that are the same sign on either end of it. So since we only have one of those, actually, we've got one right in the middle there. The inflection point is 0, isn't actually an inflection point because on either side of it, it's got a minus sign. It's negative. So because it has the same sign on either one of those, 0 is not a real inflection point. But -1 and 1 both are, so we've got 2 inflection points. So we've got our correct answer is answer choice D. Question 4, for the function f of x equals, I should say little f of x because we have a big f of x in the future. Little f of x equals 8x plus 6 over x squared, and let big f of x be the antiderivative that satisfies big f of 1 equals 1. Find big f of 2. Okay, cool. So this is getting your feet wet with integrals, antiderivatives. So as the name implies, antiderivatives are just the opposite of derivatives. So if we have our f of x, and we're trying to find big f of x, which is just the antiderivative of little f of x, f of x is just going to be the first derivative of big f of x. So big f of x prime is equal to f of x. So we basically just need to go in the opposite direction when we find the derivative of little f of x. We need to, so instead of like taking the power and moving it out front, we kind of need to go the other way around and increase the power by 1 and then take it out of the coefficient. So let's try to do that. So if we have our little f of x, that's going to be 8x plus, let me put this in a bit easier form that'll let us find this integral a bit easier. So this is going to be plus 6 to the x to the -2 power. All right, so big f of x now. How do we find this? So We go kind of in the same way. We go term by term, so we just find each term individually. So let's look at 8x now. Now, normally, you take whatever power is here, move it out front, and then decrease it by 1. Now, we're trying to go in the opposite direction, so we're going to increase it by 1. So this is a power of 1, so this is going to be 1 plus 1 is 2. And since we usually put it out front and multiply the coefficient with it, we're going to divide the coefficient by 2. So we're going to do 8 divided by 2, that's 4. And you'll see that if we do the derivative with this term, if we take the 2 out front and subtract it by 1, that'll leave us with 8x. So we know we did this right. So that is the antiderivative of the first term. Now the second one, 6x to the negative 2 power. Same logic. So we're going to increase the exponent by 1. So that's going to be x to the negative first power. And now dividing 6 by it, so 6 divided by negative 1, that's just going to be negative 6. So 6x to the negative 1 power. And you'll see, again, we can check our work. We can take the derivative of it. Moving the 1 out front would make this plus 6. And then subtracting by 1 would leave us with x to the negative 2 power. That's exactly what we have up above. So there we go. We have our full antiderivative. Oh, hang on. This isn't our full antiderivative yet, because when we do integrals, we have to add a plus c at the end of it. So why do we have to do that? Why do we have to have this arbitrary constant c at the end? So think about what derivatives represent. They represent the slope of a given line. So if we have some curve that looks like this, that is our f of x. And we have our f prime of x. I don't know what it's going to look like. Maybe it looks like that. That's our f prime of x. Now, if you were to completely forget about what f of x originally looked like, we just have our f prime of x. This just tells you what the slope of f of x used to look like. Now, fortunately, we can do the antiderivative of it and get back to the same shape of what f of x looks like. But the slope data does not tell us vertically where this function was. We don't know if it was right there, or maybe it was up here, or down there, or wherever it was. The slope doesn't tell you how high up or low vertically f of x originally was. So to account for that, we add this arbitrary constant c at the end. And this c represents this distance here. We don't know how high up it was, so we just kind of put in this placeholder c to make sure that we don't forget about it. But fortunately, we are able to find out what c is going to be here, since we're given an input and an output for one particular solution for this antiderivative. So if we go ahead and plug in both of those values, if we do 1 equals 4 times 1 squared minus 6 times 1 to the negative 1 power plus c, you can see we're left with just this one variable, this plus c. We can go ahead and solve for it and then stick it back into the original equation to find our antiderivative. So let's go ahead and do that. This is going to be 1 equals 4 minus 6 plus c. And then putting everything on the left, we'll get c equals positive 3. So we know that our true antiderivative is f, or big F of x, equals 4x squared minus 6x to the negative 1 power plus 3. That is our antiderivative. Now our final step is just plugging in 2. So doing that, we'll get, let's do it here. I got to get better at organization. F of 2 equals 4 times 2 squared minus 6 times 2 to the negative first plus 3. So this is going to equal 2 squared is 4, 4 times 4 is 16, minus, so 2 to the negative 1 power is just 1/2. So 6 divided by 2 is 3, so minus 3 plus 3. These 3's are going to cancel. We're just left with 16, so our answer choice is C. Question 5, just a limit. So what I'm inclined to believe we have to do for this problem is, let's see what happens when we plug in this 0 in for the x's. So this is going to be 1 minus cosine of 2 times 0. all over, nope, not 3, 5 times 0 cubed plus 4 times 0 squared. This is going to be, all right, so cosine of 0 is 1, so 1 minus 1 is 0. And on the bottom, all of these zeros are going to make this denominator 0. So on the bottom, we've also got 0. And hey, look at that. This is an indeterminate form, so we can go ahead and use L'Hopital's rule. So L'Hopital's rule, just a refresher, if you have if you plug in the value that x approaches and you get 0 over 0 or infinity over infinity, you can go ahead and take the derivative of both the top and the bottom. Typically, that'll change the denominator up enough to where it won't be dividing by 0 anymore. And if that doesn't work, you can keep doing it if you get another indeterminate form. And then you'll probably get your answer out of that if you no longer divide by 0. So doing that, taking the derivative of both the top and the bottom, we'll get, so let's see, on the top, we'll have, so this 1 is going to get rid of itself because it's a constant. Derivatives of constants are nothing. And then we'll have derivative of cosine of 2x. So derivative of cosine is negative sine, so this is going to be positive sine of 2x. We have to chain rule this. We have to multiply by the derivative of 2x. That's just going to be 2. So 2 sine of 2x on the top. And on the bottom, derivative of 5x cubed is 15x squared plus derivative of 4x squared, which is 8x. So looks like we're still going to have a problem because if we go ahead and plug in 0, the denominator is still going to give us 0. We're still going to be dividing by 0. But the cool thing is we can just go ahead and do it again because the top is also just going to be 0. Sine of 0 is 0. So this is 0 over 0. That's another indeterminate form, so we can just do L'Hopital's rule again. So one more time, we'll get 2 times, let's see, derivative of sine is cosine, so 2 times cosine of 2x. We have to do chain rule, multiplied by the derivative of 2x, that's just 2, so this becomes 4. And on the bottom, derivative of 15x squared is 30x, and then the derivative of, oh, okay, sorry for the pause, I thought I messed something up earlier. Derivative of 8x is just 8. All right, looks like that's all the derivatives we have to do because now if we go ahead and plug in 0, we'll no longer be dividing by 0. The denominator will just be 8. So calculating this is going to be 4 times cosine of 2 times 0 all over 30 times 0 plus 8. This is equal to, on the top, cosine of 0 is 1, and the 1 times 4 is 4. On the bottom, 30 times 0 is 0, plus 8 is 8. This is 4/8, which equals a half. Our answer is E. Question 6. Use linear approximation to estimate the square root of 99.8. All right, so linear approximation, how this goes is if you have your function that you want to estimate, it's approximately equal to f of a plus f prime of a times that's weird, times x minus a. So we have a few things that we need to find before using this formula, namely x, a, and f of x, and also f prime of x. So finding all of those, let's see, we have our f of x, our f prime of x, our x, and our a. So finding each of these. F of x, that's just going to be the original function, but without the x in it. Looks like this is just going to be square root of x because we have our square root and the weird value that we have inside of it. So plugging in that weird value is going to be square root of x. F prime of x, this is just the first derivative. So if f of x, whoops, not f prime of x, just f of x equals x to the 1/2 power, f prime of x is going to be 1/2 times x to the negative 1/2 power, which equals 1 over 2 times the square root of x. So that's our f prime of x, 1 over 2 times the square root of x. Now x, that is the original value, which is 99.8. And a is the approximated value. So if a is a value that is really close to x, but is far easier to plug into our f of x. Now, since 99.8 is really close to 100, and 100 is really easy to take the square root of, let's make our a 100. So there we go. Those are our 4 pieces of information we need to solve this. And now plugging everything in, we get f of a. So this is going to be the square root of 100 plus f prime of a. This is going to be 1 over 2 times the square root of 100. And this is times x minus a, so 99.8 minus 100. Cool, so simplifying, we get square root of 100 is 10 plus 1 over 2 times the square root of 100. So square root of 100 is 10. 10 times 2 is 20, so 1/20th. This is times, so 99.8 minus 100, that is going to be negative 0.2. Now, this is the hard part with linear approximation. It always leaves you with a fraction times a decimal, which is never fun. You always have to convert one of them to the other to make this easier. So I usually like to convert the decimal to a fraction. So let's make this 10 plus 1/20th times negative, that's just a fifth, right? 0.2 is just a fifth, so negative 1/5. Multiplying all this through, we get, let's see, 10 plus, or actually minus because of the negative. This is minus 1/100th because 20 times 5 is 100. And then simplifying this, let's see, 10 is equal to 1,000 over 100 minus 1 over 100. Now this is equal to 999 over 100, which equals 9.99, which is answer choice C. Question 7. Consider the function f of x equals x times e to the negative x. On what interval is f of x both decreasing and concave upwards? Okay, wow. So they are asking to find, so for this problem, we need to find when f of x is decreasing and concave upwards. So we need to find f of x's critical points and inflection points. Usually they just ask for one of them. So this is kind of a double whammy question unless there's some special quick way to do it that I'm not seeing. So I'm going to partition this problem into 2 halves. We'll do critical points on the left and inflection points on the right. But before we do that, we need to take some derivatives because for critical points we need f prime of x, and for inflection points we need f double prime of x. So before we do both of those, let's take some derivatives first. So if our f of x equals x times e to the negative x, our f prime of x, let's see, that's going to be, so we're gonna have to do product rule. So we've got our 2 terms, our a and our b. So product rule states that its derivative is a prime b plus ab prime. So a prime, that's the derivative of x, that's 1, times b, which is e to the negative x, plus a, which is x, times b prime, that's the derivative of e to the negative x. Now, derivatives of e are pretty simple. You just rewrite it and then do chain rule for the top if you have to. So since we just have e to the negative x, that's going to be e to the negative x. Then we bring that negative x out front and take its derivative. So derivative of negative x is just negative 1. So the whole thing is negative e to the negative x. So that's our first derivative, f prime of x. Now f double prime of x, which we're going to need for the inflection points, that's going to be, actually, before I do that, let's rewrite this to be a little easier on the eyes. So this is going to be e to the negative x plus x. Or actually, let's make that minus x times e to the negative x. So there we go. That is our first derivative. Now our second derivative, f double prime of x, that's equal to derivative of e to the negative x. Well, we already just found that. That's just negative e to the negative x minus the derivative of x times e to the negative x. Well, we already found that. That's just equal to f prime of x. So let's just substitute that back in. So that's minus e to the negative x minus x times e to the negative x. That's our second derivative. And we can actually go one step further. These two cancel out. We're just left with, let's see, positive x times e to the negative x. Hey, that's the exact same as the original. That's kind of funny. All right, cool. So we have our first and second derivatives. Now using that, we can we can go ahead and use those and find critical points and inflection points. So we'll start with the first one. Let's do critical points. We can set e to the negative x minus x times e to the negative x equal to 0. So e to the negative x minus x times e to the negative x. Cool. And now solving for x, looks like we can take out an e to the negative x from both of these terms. So this is e to the negative x times 1 minus x. Now we could set both of these terms equal to 0, make two different equations. So e to the negative x equals 0, that's that, and 1 minus x equals 0, that's that. So solving both of these independently, on the left-hand side, we can take an ln of both sides, and that'll get rid of the e right there. So this is going to be negative x equals ln of 0. Is that even? I don't know what if ln of 0. I think that's undefined. Yeah, it's just undefined. So that's not a solution. Even if we take away that negative sign and put it over there, no solutions there, so we're just left with the right one. So negative x equals negative 1, x equals 1. So this is our one and only critical point, one and only possible critical point actually. So we just have to figure out if the left side is increasing and the right side is decreasing, or the left side is decreasing and the right side is increasing. So let's do that t-chart. So we've got x, and we're using f prime of x here. That's for critical points. We put our critical point in the middle, 1, and let's put 2 points that surround it that are easy to solve. Let's probably do 0 and 2. So now plugging these into f prime of x, well, that's just 0. So doing f prime of 0, that's just equal to, let's see, this is it right here. So plugging in 0, let's see, on the left, this term, that's going to be e to the 0, which is 1. And on the right, that's going to be 1 minus 0, which is also 1. So that's positive. So we're going to put a plus right there. Now f prime of 2, that's equal to, so doing the same logic back here, e to the negative 2, that's going to be a positive number. I don't know what it is, but it's going to be positive because exponents always yield positive answers. And on the right here, 1 minus 2, that's going to be negative. And a positive times a negative is negative. So we got a plus and a minus. So we know that before 1, f of x is going to be increasing, and after 1, f of x is going to be decreasing. So we know that f of x is decreasing after 2, so that is our interval there. So that's decreasing from 2 to infinity. We probably could rule out some answer choices here, but I think it'd just be easier if we just found the inflection points either and then, overlaid the two intervals that we're going to have. So finding inflection points, similar setup. We just set f double prime of x equal to 0. So 0 equals x times e to the negative x. Solving for x, let's see. We can split this into two separate equations. So x equals 0 for that, and e to the negative x equals 0 for that. Let's see. Left-hand side, we're already done. X equals 0. And on the right-hand side is a similar situation to what we already had, where we had e to the negative x equals 0, but we showed that that doesn't have any real solutions. So that's done for. Our only potential inflection point is x equals 0. So plugging in those into our chart. So we've got our input is not 1, sorry, it's 0. Let's do some surrounding points. Negative 1 and 1 will probably be easiest. And then our output, we have to do f double prime of x for this, since we're doing inflection points. We already found f double prime of 0. That's just 0. So now for the other points, we have f double prime of negative 1. So that's equal to, looking back up here, let's see, that'll be negative e to the 1, so that's negative e, that's going to be negative. So negative right there, and then f double prime of positive 1, that's just going to be e to the negative 1, which is positive. So we got a positive down there. Now it's asking for when f of x is concave upwards, so that's going to be this interval here. So we know that f of x is going to be concave upwards starting at 0 and going on for infinity. So 0 to infinity. So the interval, well, first off, hang on. We have our two intervals here. The left interval is when f of x is decreasing, and the right interval is when f of x is concave upwards. So to solve our problem, we just have to find the interval that encompasses both of them, the interval where both of them apply. And this one is actually the whole thing, because this one just encapsulates all of the decreasing interval. So the decreasing interval must be the one true interval that we're looking for. So answer choice C. Question 8. A storage crate is to be built in the shape of a box with a square base. It is to have a volume of 10 cubic feet. The material for the base of this box costs $4 per square foot. The material for the lid of the box costs $1 per square foot, and the material for the sides of the box costs $2 per square foot. If A is the width of the crate and H is the height, what are the dimensions of the crate that minimizes this total cost to build the crate? All right, this is a grade A related rates problem, so let's draw this out to make our lives a whole lot easier. We have a crate, which is just a rectangular prism with a square base. So let's do A times A for the bottom. And then it has some height, which is in terms of H, and then its top. And it's a filled top. It's not an open top. Sometimes with these box problems, they like to have an open top or whatever and ask you to calculate something without it. But we do have a filled-in top. And what's asking is, before I move on, it has a volume of 10. So volume equals 10 cubic feet. All right, so what is it asking? It's asking to minimize the total cost of this box based off of these material prices per side of the box. So let's actually fill those in really quick. So the top of the box, that's $1 per square foot. The sides of the box, let's see, each of those are $2 per square foot. And then the base of the box, that's going to be $4 per square foot. So knowing all that, how do we minimize this? All right, so first thing we do for related rates problems, we determine what formula we're going to use. And sometimes that's the hardest part of the related rates problem, because sometimes the formula that instantly pops in your head that you want to use is not the one that you want to be using. Like, for example, for this one, when I was reading through this problem, we had a lot of information about the volume of the box and also its side lengths. So I instantly thought, okay, we should probably use the volume formula, where the volume equals all three side lengths multiplied together. So that'd be a squared times h. But that won't actually work because it doesn't factor in these costs at all. We're asked to minimize the cost of the box, so we need some formula that incorporates cost. For this problem, we can actually just kind of build our own. We can define some formula like C equals, and then whatever we determine should go after it, where C equals the total cost to build a box based off of A and H. So what should this formula equal? Well, there's three different definitions for how costly this box should be. There's the base of the box, there's the lid of the box, and there's also the sides of the box. So based off of those three sides, we can determine what the total cost of this box is. Now for each of these, what are they? So let's see, for the base of the box, that's $4 per square foot. And determine the base's total area, that's just A times A, or A squared. So the cost of the base is going to be 4A squared. Now for the lid, it's the same thing, but it only costs $1 per square foot. So that's just going to be A squared, 1 times A squared. And then for the sides, well, the side is $2 per square foot, but we have 4 of them. So 2 times 4 is 8. So it's $8 per square foot, and to determine the side of a box, that's A times H. So 8AH for all of the sides combined. And that is our cost formula. That's what we will eventually take the derivative of. Now, before we do that, we can do a couple of things. First thing is we can combine both of these. 4a squared plus a squared, that's just going to be 5a squared plus 8 times a times h. And then for this 8 times a times h, what if we were to just put everything in terms of a? That would probably be a lot easier to take the derivative of. So we can get h in terms of a by using the volume formula. Since the volume equals 10, we can just go ahead and divide both sides by a squared to get h. So h equals 10 over a squared. We can just go ahead and plug that in down here. 10 over a times h, or 10 over a squared, I'm sorry. And now we have everything in terms of a. So one last thing, let's make this a little cleaner. This is going to be 80 over a, and now we're in a pretty good state to take a derivative. Actually, no, we aren't. I'm making a lot of jumps here, but this is going to be 80 times a to the negative 1. That's easier to take a derivative of. We can just do power rule. All right, finally, let's take this derivative. So c equals, putting the 2 out front, that's going to be 10 times a. And then for the second one, we move the negative 1 out front, so it's going to be minus 80 times a to the negative 2 power. So that's the same as 80 over a squared. Now, solving for a, if this all equals 0, let's see, we can add 80 over a squared to both sides. So 80 over a squared equals 10a. Then we can cross multiply. So if this is a 10a over 1, we can go ahead and multiply, cross like that, and then get our answer. So the first one, 80 times 1 is just 80, and a squared times 10a is 10a cubed. So dividing both sides by 10, we get 8 equals a cubed. And then cube rooting both sides, we get a equals, not 8, a equals 2. So based off of that, we already have our answer. It's a. And to double check that, we can just use the volume formula up here, 10 equals a squared times h, and see what h should be. And it should be 5 over 2. So 10 equals 2 squared times h. So 10 equals 4h, and dividing both sides by 4, 5 over 2 equals h. Cool, we got the right answer. A is correct. Question 9. Find the number c that satisfies the conclusion of the mean value theorem for the function f of x equals x plus 1 over x on the interval from 1 to 3. Okay, okay, cool. Refresher on the mean value theorem. So the mean value theorem, what that says, just in words, is if you have a function like this is an example, and you pick any 2 points on it. So let's say you pick that point and that point. If every point in between is continuous and differentiable, which it is, if you draw a line connecting the 2 points, that slope of the line will have to occur on some other point on the original graph. So in this interval here, there has to be some point where when you take its derivative, it'll have the same slope. In this case, it'll probably be somewhere right around there. So when you take its derivative at that point, it looks like its slope will kind of go like that, which is the same slope as the original line there. They're parallel. So that's what the mean value theorem states. Now what this is asking for, the number c that satisfies the conclusion, that's just saying, so we're going to find this slope of the line that we draw here, and when we find that slope, we'll get some number. We need to find that x value that that point occurs on. So to do that, first we need to find what the slope of this line is going to be. So we need to do the mean value theorem on f of x from 1 to 3. So to do that, there's a formula for it. So you've probably seen before, back in like algebra or something, you've got y2 plus y1, I'm sorry, y2 minus y1 all over x2 minus x1. Well, this is actually just going to be the exact same thing. This is going to be f of b minus f of a all over b minus a. So you notice that the f of x's are the same as the y's because they're both outputs. and B and A, this is our A and this is our B. So going in and plugging all those in, let's see what we get. So f of B, that's going to be, B is 3, so it's going to be 3 plus 1/3, minus, so f of A is 1, so 1 plus 1 over 1, all over 3 minus 1. Let's see, on the top here, this left side, that's going to be 9/3 plus 1/3, that's 10/3, minus, I would say 1 plus 1 is just 2, which is 6/3. I'm setting all these up in a weird way just so that they all have the same denominator, so it's easy to combine them later. And on the bottom, we have 3 minus 1, which is 2. One step further, let's see. 10/3 minus 6/3 is 4/3, all divided by 2, so that equals 2/3. So we know that the slope of this line is going to be 2/3. And now knowing that, you can use that to find the x value of the point where its derivative equals 2/3. And to find that, we can just take the derivative of f of x and set it equal to 2/3. Doing that will leave us with one variable, x, and we just solve for it. So what is the derivative of f of x? So derivative of x, that's just 1. And then the derivative of 1 over x, well, 1 over x is the same as x to the negative 1. So doing power rule there, we move the negative 1 out to the front and then reduce it by 1. So that's going to be minus x to the negative 2, or in other words, 1 over x squared. So that is the derivative, and now solving for x, let's see, we could subtract 1 from both sides. So this will be negative 1/3 equals negative 1 over x squared. We can drop these minus signs, multiply everything by negative 1. And then we can, since we've got two fractions here, we can just flip them over. We can take the reciprocals of both. That won't change anything. So we've got 3 equals x squared, and x equals, technically it'll be plus and minus square root of 3, but negative root 3 is outside of this interval, so that doesn't concern us. We're just left with positive root 3. We have answer choice D as the correct one. Question 10. You are the owner of a rectangular orchard adjacent to a straight river. You have 600 feet of fence that you want to use to enclose this rectangle. No fencing is required along the river, and x is the length of a side perpendicular to the river, and y is the length of the side parallel to the river. And we want to find the values of x and y that will maximize the total area. All right, cool. So we have, let's draw this out. So we have our river. Let's see, let's put this at the bottom. Just to, for dramatic effect, it's got fish in it. So you know it's a river. And then we have our fence building off of it. So this fence doesn't have any fencing running alongside the river. I guess maybe this fence is used to keep animals that can't swim in it. So you don't need to build a fence along the river. And let's see, we've got x is the length of a side perpendicular to the river. So it's going to be these sides right there. And then y is the other side. It's the side parallel to the river. And knowing all this, we have 600 feet of fence that we can use to build this thing. And we need to maximize the enclosed area. Cool. So this is a related rates problem. So the first thing we do for these is to find the formula that we should use to calculate this. Since we're given we're trying to find area and we're given two side lengths, we can just use the volume of a rectangle formula. A equals x times y, the two side lengths. This will work for us, but we do need to make one adjustment to it. These types of related rates problems only work if you have one variable on each side. So since we have an x and a y, that won't really work. So we need to put the right side in terms of one of the variables. Now, since maybe we could just make everything in terms of x and try to turn this y into something else. So to do that, we can just use some of the information given to us in the problem. So let's see, it said that we have 600 feet of fence to work with. So let's do 600 equals, what does it equal? So we've got two x's and one y, so it's going to be 2x equals, or 2x plus y. So 2x plus y must equal 600 feet. Now to put this in terms of y, we just subtract 2x from both sides. So, So we've got 600 minus 2x equals y. So let's substitute that in. A equals x times 600 minus 2x. We could distribute everything, so A equals 600x minus 2x squared. And now we can take a derivative, so of the right side. So we've got A equals, let's see, derivative of 600x is just 600, and then the derivative of 2x squared is minus 4x. So that is our derivative. Now we can go ahead and set it equal to 0, and we can find this critical point because we're asked to maximize this, and we just took a derivative, so let's do a critical point thing. So solving for x now, looks like we can add 4x on both sides. So 4x equals 600, and then dividing everything by 4, x equals, so 600 divided by 4, that is 150. There we go. That is the value of x that we want. Now we just have to find the value of y. We can just use what we found up here, where 600 minus 2x equals y. So 600 minus 2 times 150 equals y. And then putting everything together, we get 300 equals y. So this is answer choice B. Now, before you click off the video or before you click next to the next question, I want to tell you something really cool. These types of problems where you've got a rectangular fence where one of the sides of the fence is along a river and it doesn't have to be included, you can cheat it every time. And what you need to know is that the x, the perpendicular side length, will always be 1/2 of the parallel side length. So in this case, that's what happened. X is 150, and 150 times 2 is 300. That checked out here. See, what you can do is just run through all the answer choices, mark off all of the ones that don't fit that, and you'll usually just be left with the one that works. And if there's multiple, you can just go from there and see what area you'll get from that and determine which one is the biggest. But in this problem, we went and did it using standard related rate stuff, which you should probably still use and definitely still know. But if you ever are crunched for time on these exams, you can use this one trick for these fence problems and it'll save you some time. Question 11, evaluate the limit. I don't like this question just because it's a knowledge test. I don't even know if you know how to do this limit yet. But what I think they're testing you on is if you know this one specific limit. So I'm talking about the limit as x approaches 0 of 1 plus x to the 1 over x. This is really similar to what we have up here, but there's no 3 next to the x inside of the base. What this actually equals is e. I think they teach that in class. I remember I had a Calc 2 recitation question about this. So I think you're kind of expected to know it. And also, I guess what you're also expected to know is that whenever you substitute a constant in here, so in this case we have 1 plus 3x, that just adds it as an exponent. So this 1 plus 3x is going to turn this into e cubed, which is actually the answer here. And that's why I don't like this one, because it's just memorization of facts. It's not working through a problem. It's just remembering that, hey, this one limit equals e to the coefficient of x that you have in the base. So that's why I don't like it, but that's how you get the answer of A here. Question 12, approximate the area of the region bounded by the graph of f of x equals 4x squared plus 1 and the x-axis by dividing the interval from 0 to 2 into 4 subintervals to find the left Riemann sum. All right, so Riemann sums, these are pretty, I don't know how useful they are, but they're not super hard to do. It's mostly just basic like math, just adding and multiplying and stuff. It's not like a derivative that you're doing or anything. It's just remembering how to do them. So Riemann sums, I'll explain what they are here. Let's just have an example function that looks like this on the interval, and we're asked to find the Riemann sum from 0 to, let's do the same interval, even though it's a different problem. Let's do 0 to 2. So we need to find this area down here. Now, normally we just take the integral, but it is specifically asking us to do a Riemann sum, which basically says let's do the same number of subintervals too. Let's do 4 subintervals. What we can do is just choose 4 points on the graph and then construct rectangles using them. So let's construct a rectangle there. Let's construct a rectangle here, a rectangle here, and a rectangle here. So it looks like we've got the area here, we've got the area here, and then the areas of these two. And then what we can do is just add up all of the areas, and it'll roughly be the same as this total area here. So I say roughly, it's not going to be the exact thing, but it's a lot easier because it's just a bunch of rectangles. Those aren't too bad to calculate at all since it's just length times height. So to do these to actually do this for our problem, let's see, what we would do is, let's do sum equals, actually we don't really need an equals. Let's just do, all right, so we have 4 subintervals and they're on an interval that is 2 units long. So we do 2 units minus, or divided by 4 subintervals. We get each rectangle is going to be 1/2 unit size. So we're going to multiply everything by 1/2. And then what is the height of each interval? Well, that's just going to be this point that we found. That's going to be the f of x of each point. So that's going to be f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. Those are those 4 x values for those 4 points there. And then when we add all of them up and then multiply it by 1/2, that's going to find the sum of all of these rectangles. So let's go ahead and calculate this. 1/2 times f of 0, that's going to be 1. F of 1/2, that's going to be, let's see, 1/2 squared is a fourth. 4 times 4 is 1. 1 plus 1 is 2. F of 1, that's going to be 4 plus 1 is 5. Plus f of 3/2, that's 9/4 times 4. That's 9 plus 1 is 10. Adding all these up will be 18. 18 times 1/2 is 9. So that is the answer here. That is the total area of all 4 of these rectangles that we've drawn out using the Riemann sum.